Okay, we will wait for 2 to 3 more minutes, then we will begin the session. Okay. So all of you, are you now able to see the screen now?
Yes.
Okay. Okay. We will start. So how was the quiz 2 exam? How was your exam?
It was good, ma'am.
Okay, good. Just messed up. Why? Bala? Bala Murugan, what was the problem? Like, did you find the questions to be difficult or what? Okay. That's a serious issue then. Okay, so have you seen the lectures, recorded lectures?
I have not done that yet, ma'am. I just finished the stats for week 11, but haven't finished that one. So
Okay.
I have not started the other one.
Okay, okay. Okay, so I will cover whole week 11 portion, almost, and then you can start watching the lectures. Maybe today I will not be able to cover the whole week 11 portion. So tomorrow I will cover some of the portion of week 11. Then we will solve some problem. Okay, and today we will cover some of the portion. Okay, so we can now start, right?
So tomorrow, when you say tomorrow, ma'am, when is the class tomorrow?
Okay, so we will schedule a class tomorrow evening at the same time, 8
Wonderful.
to 10.
Thank you. Thank you.
When is the week 11 assignment deadline, graded assignment deadline?
Next
It's on
Wednesday.
11th.
11th means next Thursday, right?
No, 11th means
Upcoming Wednesday.
Upcoming
Wednesday.
Wednesday.
Okay, okay. So tomorrow we will cover rest of the portion and we will solve the problem. So then we will get one day. So in this one day you can look at the problems, assignment questions. Then again we will discuss them Tuesday. Okay. Then you can submit your graded assignment Wednesday easily, right?
Right, ma'am.
Okay. Yeah.
I'm not cover the week 10 portions, not what. Is it okay to continue with week 11 lecture? Or
No, you should first go through the week 10. But
Okay.
still, I will start with some basic definition. I will give you the definition. So you just stay in the session.
Okay.
You can at least get something from the session. Okay. So when you will see the recorded lecture, you can recall the thing and it will be helpful for you.
Okay, ma'am.
So it's better to stay in the session. Okay. So we can now start, right?
Sure, ma'am.
So let me just quickly summarize first. So what are the content we are going to cover today? So in your week 10, you read about DAG, right? DAG means directed acyclic graph. right? So you remember what a graph is. So we just denoted or noted a graph with like some a collection of like a combination of set of vertices and edges, right? That means graph is basically some vertices. So these are called vertices, and we will take the edges joining these vertices. So this is you can consider this as a graph. And directed graph means we will have a direction like that, right? That we already know from the week 10 content, right? So directed acyclic graph is like we will not have any cycle in our graph, okay? And what a cycle is, as we know, that means repetition, right? So if this 0 1 2, then we can see we have a age 0 to 1, then we have another age to 1 to 2, and another age from 2 to 0, right? So it's clearly forming a cycle, like we have a repetition, right? So this is called cycle. And directed graph means we will have a direction. And if we don't have the arrow, that means we don't have any direction. That means we can go from this vertex to this vertex, and we can also come from this vertex to this vertex, right? So directed acyclic graph means you will have a graph which is directed and which doesn't contain any cycle in it, right? So for example, this is a, you can consider this as a directed acyclic graph, right? So we can see this graph has direction. That means everywhere when we are drawing a edge, we are considering an arrow, right? That means the graph has direction, and clearly there is no cycle, right? So this is a example for a directed acyclic graph, okay? So in short, we will call this type of graph as DAG or DAG, directed acyclic graph. Okay, am I audible?
Yeah, ma'am.
Yes, ma'am, you're audible.
Okay, okay. So if you are getting any doubt, just unmute yourself and let me know. Okay, I will not be able to see the chat box. Okay.
Sure.
Okay. So this is the concept, and in the last week we knew some of the process or algorithm using which we can calculate the shortest path in a DAG, right? We practice some of the algorithm like that. In this session, we will start a new thing. Like suppose we have a DAG and we want to calculate the longest path. Okay, we are done with the shortest path. We are done with the shortest path. Now our problem is to calculate the longest path in a DAG. Okay.
So, ma'am, when you say shortest path, you're referring to the breadth first search, is it?
Yeah, your
Okay.
or DFS, both the process, right? So we learn about these two process, right?
Okay. DFS also gives the shortest path, is it? I mean,
I don't think so, ma'am. Like sometimes it will and sometimes it won't, I guess.
Okay, but
DFS.
both the process we use to find the shortest path, no? Am I right? Maybe wrong.
Actually, the professor mentioned DFS is not used for shortest path. Only BFS is used.
Okay, that may be the case. But what I remember, we are also using the DFS to finding the shortest path. I mean, BFS and DFS both. Okay, so let's not discuss about them right now. I may be wrong because I am also learning graph theory with you. So, okay. So in this session, our first problem is to find the longest path. Okay. So we will compute the longest path for a DI. So you know what our topological sorting is, right? So whenever we have a directed graph, in a topological sorting, we basically consider a sequence with respect to the dependency, right? So we know what a topological sorting. So we will use the topological sorting to calculate the longest path for a DAG. Okay. So basically, what a longest path is, first of all. So just for example, if we take a graph like that, okay, suppose we want to reach from 0 to 6. Okay, suppose this is our goal. Now we can consider two ways, right? I mean, from 0 we have two outgoing edges, right? First, which is going to 1, that means your 0 1, and the second outgoing edge is 0 5, right? That means this edge. So if we follow this path, so first we have to go from 0 to 1, then 1 to 2, then 2 to 3, then 3 to 6, right? That means we have to use 4 edges here, right? And if we follow this way, then we will first go 0 to 5 and then 5 to 6, right? That means 2 edges, right? If we follow this path, then we will use 2 edges. And if we follow this path, then we have to use 4 edges, right? Now, it is clearly obvious, right? We have to use 4 edges. I mean, if we want to find the longest path, that means the second path, which is using 4 edges to reach from 0 to 6 is the longest path, right? Because we are using more edges here. Okay. So whenever we have a directed graph, which is not a weighted graph, for this type of graph, longest path means we will consider the path which contains most number of edges. Okay. So what a longest path is, the concept is now clear, right?
Yes, ma'am.
Okay.
Yes, ma'am.
Now we will check the process. I mean, how can we calculate a largest path for any graph? Okay. So first we will initialize this process. Like when we'll have in degree, suppose I is our vertex. Okay. I is one of the vertex. And suppose in degree of I is equals to 0. So we know what a in degree is, right? When we are saying that in degree of I is 0, that means there is no incoming edges to I, right? So it will automatically means that right? So in degree means we consider all the edges which are incoming to I, and out degree means we consider all the edges which are outgoing from I, right? So whenever we are saying for the vertex I that in degree is 0, that means there is no incoming edges, right? So for this type of thing, we will consider the longest path to I is equals to 0. Okay. Okay, so this we will always keep in our mind. Okay, whenever for a vertex the in degree is I, we will always consider the longest path to I equals to 0. Okay, now what for the vertex when the in degree of some vertex is greater than 0, that means for that vertex we have some edges which are incoming to the vertex, right? So if in degree of I is greater than 0, that means there is some incoming edges to I. Okay, in that case what will be the longest path to I? In that case we have the definition. The longest path to I will be 1 plus maximum of okay. So this is the formula. Okay, that means for a directed graph, when we have a vertex I with in degree 0, we will immediately imply the longest path to be 0. Okay, and if the in degree is 1, I mean sorry, greater than 0, then then we can find the longest path using this formula. And this formula says what? Now 1 plus maximum of longest path to j, where j comma I belongs to E, and we know that E denotes the set of all edges, right? And j comma I means the edge from Z to I, right? So if we have a vertex I, then suppose the in degree is greater than 0, then obviously there are some edges which are incoming to I, right? So it can be some j, it can be some k, it can be some l. Okay, suppose for these 3 edges we have the for these 3 vertices j, k and l, we have a incoming edges to I. Okay, so in that case we will consider for so in this set we will have j comma I. So we have j comma I, we have k comma I, and we have l comma I, right? Because of the direction. So we have to consider all the cases. Okay, so now we will consider the path for all the 3 vertices separately. Okay, then we have to choose the longest path or the maximum among all the paths. Okay, so this is the algorithm, and let us solve example so that you can get it properly. Okay, so this is the algorithm. Now we will solve the example. Okay, so suppose we have this graph 0, 1. Okay, so okay, so our step 1, that means step 1 is we will mark we will initialize the in degree. We will update the in degree for all the vertices. And we will initialize the longest path as 0 for all the vertices. Okay. That means we will write 0 instead of the longest path. Okay. Suppose longest path is we will consider as a blue pencil. So we will initialize it with 0. Okay. That means initially we will give 0 to all the vertices. Okay. And this is done, right? And then we have to update the in degree. Now one of you just unmute yourself and tell me the in degrees of each of the vertices. Okay. So what is the in degree for 0?
0.
Yeah, right. And for 1?
0.
Right. 2?
2.
2.
Yeah. 3?
1.
Yeah. 4?
1.
1 on
Yes. 5?
2.
Yeah. 6?
1.
7?
4.
Okay. So we are now done with the first step, right? So our first step was we will update the actual in degrees and we will initialize the longest path as 0. Okay.
Ma'am, just a quick question. So the longest path is from the root, is it? That's what we are saying. The
Yes,
longest
yes.
from root.
Yeah.
Okay.
From the root. Okay. So we can consider the source or the root with like some specific vertex. Okay. So you just tell it. Here we can consider both like 0 and 1. Okay. Because we have the in degree 0 for both 0 and 1. Okay.
Okay.
Yeah. Okay. Now the second set is we have to create a list based on the steps. Okay. So the list is we will consider the vertices. Just let me denote it with V. And then we will consider the longest path. Okay. Just we are denoting it with L. Okay. So we now know that the vertices having the in degree 0, we have the longest path as 0, right? That means for 0 and 1, we get the longest path, right? Any doubt? No, ma'am. Okay. So for the vertices, both of the vertices 0 and 1, we have the in degree of both 0 and 1 is 0. So that means the longest distance of both 0 and 1 is 0, right? So we know the longest distance of 0 and 1. So we will update them in our list. Okay. So what is the next step? Then we will move to, after the updatation, we will move to the next step. Okay. Next step is we will remove the vertices with in degree 0. That means from this picture, we will remove 0 and 1. Okay. Then we will keep the longest distance as same and we will update the in degree. Okay. Okay. So this is the second step. Now, first, we have to remove the vertices with in degree 0. That means we will remove 0 and 1. Okay. Then we will have 2, 3, 4, 5, 6, and 7. Right? Okay. So we remove the vertices with in degree 0. Okay. Then we have to, what is the next thing? We have to update the in degree, right? So once we remove the in degree 0, like 0 and 1, then the in degree of 2, 3, and 4 will be automatically updated, right? So what will be the updated in degree? This will be 0, right? For 2, 3, and 4. The updated in degree will be 0, right? Because if we remove the 2 points, 0 and 1, then there is no edges which are coming to these 3 points, right? 2, 3, and 4. So updated in degree will be 0. Okay. And then we will keep the longest path as it is. Okay. So this will be then okay. So sorry, not as it is. We have to update the longest path too. So we just check this step and we have to check this, right? We are done with the in degree. So we updated the in degree. Now we have to update the longest path, right? Now we have to follow the definition for longest path. So when the in degree is greater than 0, we have the definition for longest path is this, right? That means 1 plus maximum of this, okay? So we have to update the longest path for 2 first, okay? For this vertex, we will update the longest path, okay? So what is the longest path for 2? This is 1 plus maximum of the longest path. So for 2, we have only 2 options, right? 1, 0, 2, and the second edge is 1, 2, right? Because for 2, we have only 2 incoming edges, right? So we will consider maximum of longest path of 0, 2, comma, okay? Okay, I'm just following the definition. Okay. So if I check the list, then we have the longest path for both 1 and 0 is 0, right? So we will just put them here. Okay, so we will get then 1 plus max of 0, 0. That means 0, right? So this will be basically 1. So the longest path of 2 now become 1. Okay. So once we know the longest path, we will update the longest path as per the rule. Okay. So then this become 1. Similarly, we will calculate the longest path for 3. Okay. So how to calculate the longest path of 3? For this, we have to check the incoming edges to 3, right? So for 3, we have only incoming edges, which is from 0 to 3, right? That means we have to take 1 plus the longest path of 0, which is 0, right? That means we have 1. Is it clear?
Mhm.
We will just use the definition because we have only one option, longest path of 0. So we will just take them. Okay. This will be 1 plus 0. That means 1. Okay. So the longest path of 3 now became 1. Okay. Is it clear?
Yes, ma'am.
Okay. Now just then let me know what is the longest path of 4.
1.
One only.
Yeah, right. 1. Okay. So we are done with 2, 3 and 4. Now we have to update the same to 5, 6 and 7 also, right? So what is the in degree of 5? It's again 2, right? And for 6 it's 1 and 7 is 3, right? The updated in degree, right? So what is the longest path of 5 now? We have to apply the same rule, okay?
2, ma'am.
Okay. So longest path of 5 is 1 plus max. So we will check the incoming edges, right? So max. So we have this two vertices, 1, 2, and the second one is 3, right? And for both the vertices, we have the longest path as 1, right? So the maximum will be again 1. So we have 2. Okay. 6 for 6. What is the longest path to 6?
3, ma'am.
Right. And 7?
4.
Correct. Okay. So once we are done with it, again, we have to list the vertices along with their longest term, which have the in degree 0 as per the rule. Okay. So we can see for the vertices 2, 3 and 4, 2, 3 and 4, we have the in degree 0, right? So then we will list up them, right? So we will list up the vertices 2, 3 and 4, and 1 is the longest path for all 3 vertices, right? So our list, the updated list will become this. Okay. Again, we will repeat the step 2. Okay. What is the step 2? Again, we have to remove the vertices which have in degree 0. Then we will update the in degree and update the longest path. Okay. So we have this picture. We have to now remove 2, 3 and 4. Okay. Then we have 5, 6 and 7. Right. Now we have to update the in degree. So what will be the in degree? 0, 1, 1, right? And what will be the longest path? So we have 2 here for 5. So it will remain 2, right? From this picture, it will remain 2, right? Any doubt? Okay.
Where is
No,
that
ma'am.
What?
one coming from? Ma'am, where is that 1 coming from? That 5, we already noted that in the last step, we already noted that the longest step was 2 till 5.
Yes.
So when you rotate with blue in the bottom, again you rotate with the blue, right? No, just below that, you wrote one sentence. I know below that. Yeah, here you have written longest path to P is equal to 1 plus max of 1 comma 1.
Yes.
Now 1 plus 1, 2.
Yes.
We just have now 3 indexes in vertices, right? 5, 6,
Yeah.
7. Because we removed 2, 3, 4. Now where is this max of 1 comma 1 is coming from?
Max of 1 comma, okay. So max of 1 comma 1 I took because see, we are calculating the longest path to 5, right? So
Yeah.
to do this, we have to first check the number of incoming edges, right? So we have these 2 edges, right? 2 comma 5 and 3 comma 5, right?
We already removed it, didn't we? Like we
No.
removed.
We calculated this step to calculate the longest part in this graph. After this is before removing these 3 points.
Okay. Yeah, this step is clear to me. If 2, 3, 4 is to be included, then I have understood.
Yeah. So I did this step to calculate the longest path in this graph. Okay.
Okay, this is fine. Okay.
Okay. So we don't have to now update the longest path for the vertex 5, right? So obviously we can see from this graph it will become the same. right? So for the vertex 6, do you need to update it? No, right? Because we have only one incoming edges, which is form 5, right? And for 5, we have the longest path as 2. So as per the rule, we have to add 1 with the longest path of the last vertex, right? So it will remain 3 and it will automatically remain 4, right? So again, we have the in degree 0 for this 5, right? So we have to note down the vertex 5 in our list with the longest path, okay? So then we have 5, 2, right? The vertex 5 along with the longest path 2. So again, we have 0 in degree for the vertex 5. So as per the rule, we will remove them. Then we will get 6 to 7. And we will update, again, we will update the in degree. So in degree will be 0 and 1. Sorry, we are using the yellow color. So this will be 0 and 1. And this will be 3 and 4. Okay. So in the next step, again, we will remove this and we have to add this in our list, right? So we will have 6, 3. Again, following the same step, we will remove the vertex 6 and only we will have the point 7, right? With in degree 0 and longest path 4. This is the final step, right? So finally, we will then update our list and we will enlist the point 7, 4. Okay. So then 7 is the number with the longest path 4. Okay. Any doubt? This is the process. We can also check by the graph. I mean, once we have the graph, suppose we want to reach from 0 to 7. Okay. So what are the ways we can use? So first, we can go from 0 to 4, right? Then 4 to 7, right? So this is using 2 paths. Again, we can go from 0 to 2, then 2 to 5, then 5 to 6, then 6 to 7. This is using 4 vertices, right? We can go from 0 to 3 and 3 to 4. This is again using 2 vertices, right? So we can clearly say the longest path is 4, right? The length of the longest path is 4, right? From the graph. And from using the algorithm also, we arrive to the fact that the length of the longest path is 4. Similarly, for all the vertices, you can check from the picture and you can match them with the list. Okay. So is the process clear to all of you?
Yes, ma'am.
Ma'am, this is clear. Thank you.
Ma'am, just a question here. Do we get this Q-based questions in exam also, where this Q we have to generate or we have to learn this algorithms?
Like cube means, what are you saying?
Ma'am, this table that you have generated after completing this algorithm. So do we get table like this where we have to write the longest path? For example, they have given vertices.
Okay. So you don't need to write the table in the exam. This is for your calculation. Okay. We will ask you some question, and to solve this type of question, you may have to use this procedure, this algorithms. In that case, you may have to create the tables, but for yourself. Okay. You don't need to write the tables in the exam. Like, we will not ask you to write the whole table in the exam, obviously, right? So we will have some question. So for that, you may have to calculate the table sometime. Okay.
Okay, ma'am. Thank you.
Ma'am, one more point that I've observed is this method is essentially just used to find the longest path to a node. It does not
Yes.
necessarily tell me that it is starting at this node. It can start at any of the root vertices that has been defined in the graph.
Yeah, like you can, root means we are meaning it like with in degree
No,
0.
Correct.
Yeah.
Right.
Yeah.
Right.
So it can be anything with in degree 0. I mean, for any root. Also, you can like observe from the graph too. If I want to find the distance from 1 to 7, then it is also again 4, right? Or 6. You can like 1 to 2, then 2 to 5, then 5 to 6, then 5 to 7.
No, agreed. But what I'm trying to say is, let's say if you remove the cyclic direction from 1 to 2, in that case, then it isn't necessarily that we can reach 7 from 1. Like there can be a situation where 1 to 7 is shorter than the path from 0 to 7.
No. Then the case will be something different. Now, in that case, we have to then recalculate this thing, and we will have the in degree of 2 different, right?
No, ma'am. That is right. That is, wait, let me just think through. So, my statement was that if you start at any of the nodes which has an in degree of 0, this specific algorithm only gives you the longest path to reach a specific node, but it never tells you what is the starting node from where you have come. It doesn't tell you about that. So it can basically start, I mean, it can happen that the longest path exists from 0, or it can exist from 1, or I mean it's the same path from both, like same longest path from both. But that's what the statement that I'm trying to make based on this algorithm so far.
Okay, so the thing is, I mean, we don't know about the specific point, but yeah, it's again like we know the root, so we are calculating from root. Here we are considering it 0. So you are saying if I remove the age from 1 to 2,
Correct.
then what will be the case, right?
Correct.
So in that case, I think the topological sorting will be different. I mean, then 2 will not be like dependent on 1, right? So
Correct.
we will get something different. I mean, the
Agreed, ma'am. But what I'm saying is the sorting will be different, but your answer, I mean, the answer might like, then in that case, it will be from 0 to 3, 3 to 5, 5 to 6, 6 to 7. Then again 1, 2, 3, 4. So again, the answer is still 4, but it is only from 0 in that case, right? The answer, this answer to the 7 is still the same, even in that situation. That's what I just meant.
Yes, yeah. Your doubt is correct. Okay, just give me 2 minutes. Let me think about it.
Sure.
Okay, actually, I listed your doubt. Okay, right now I cannot find the exact logical explanation because I am also learning the graph theory. I just told you. So in the next class, I will definitely clear your doubt. Okay.
What's the question?
It's okay, ma'am. I just put this observation in front of everyone.
That is very good. You should do this type of thing.
Ma'am,
During the
could you
class.
repeat what was the
Yeah, sure.
observation?
The observation is like following this way, we are finding the longest path, right? So longest path from the vertices. So here, if we we are considering the vertices with in degree 0 as the root of the system, of the graph, right? So when we are finding the longest path, it can be from 0, it can be from 1, right? Because the particular point is not mentioned here, right? So we can take 0 and 1 also. So if we just remove the edge 1 comma 2, okay, then the longest path from 0 to 7 will be 4, right? But the longest path from 1 to 4 will not be 4 in that case.
You're removing the edge from the 1 to 2, right?
Yeah, we have a edge from 1 to 2. If I just remove the edge from 1 to 2, then we only have this edge, right? Only via this way we can reach to 7, right? In that case, the longest path from 1 to 7 is not clearly possible, right?
Yes, ma'am.
Okay, wait. Maybe one thing is like our when we are finding our problem, I mean the longest path, then our graph should be connected. Okay, this is a fact. So if I remove the edge 1 comma 2, then our graph will not be connected anymore.
Yeah.
Maybe
Because what here, yeah, you are correct. So 1 to 2 only we cannot remove it. If you are taking out 1 to 2 also is supposed to take out, 1 to 7 also is supposed to take out. So entire 1 you have to remove from all the edges.
just repeat once.
When you're considering the root node as 0 or 1, either whatever. So you have to take out all the outgoing edges.
Yeah.
You cannot take only 1 comma 2 only or 1 comma 7 only one by one.
No, but why do we want to take out all the edges? What I proposed was we are only
Yeah.
taking out the
If that is because that is a theory saying this topological sorting is supposed to learn. So topological sort is what is saying from 0 to 1 if it is connected, we have to remove that 0 to 1 all the edges, whatever the 0, the incoming edges is 0, so that we have to remove all the edges of outgoing of that particular topological sort. So whatever the overall concept here is, so you just fix the graph, don't remove anything. So you just normally logically think for the 6 from 0 to 1 or 1 to 0, whatever the maximum longest path is 3 only. The 7 maximum longest path is 4 only. Maximum, so each and everything is defined in that way. So like that works.
Correct.
So you have to once.
Yeah. I guess I can explain. I mean, what he is saying, if I don't consider this graph, instead of this graph, if I consider the graph like that, 3, 4, 3, 4.
Ma'am, now you're drawing edges without 1 and 2, right? 1 and 2 connecting,
Yes,
right?
yes.
Then there is no problem, right? 0 to 7 is the longest path.
Right. Okay. Suppose this is the graph.
Yeah.
Then what happened? Like in that case, we have both 0 and 1 as in degree with 0, right?
Yes.
And
still it is like longest path is for 7 is 3.
How?
Yeah, 4. Sorry, 4. 0 to 2, 2 to 5, 5 to 6, and 5 to 7. So 4 edges are connected. So still you can yes. But that graph is different, ma'am. You have to take out the entire outgoing edges, ma'am. When you are considering that is topological sort is when you are removing it, if it is in degree 0, you have to remove entirely all the outgoing at a time. You cannot take one by one. This graph is different story. Yeah. This status path is 1 to 7.
This graph is completely different.
Different.
Yeah. It doesn't have any connection with the previous one.
Yes. So still it is for 7 is you just whatever we are what the
so what
formulation.
he is saying ki the longest path from 0 to 7 is 4 still. But what about the longest path from 1 to 7?
Yeah. So that won't exist, ma'am. That's what I'm saying. That won't exist. This algorithm only gives us the path to
Longest
long
path.
path to reach a node. It does not matter from where you are
Yes.
coming. It gives you that answer. That's it.
Yes, correct. That is true. It doesn't matter where you are coming from, but it is maximum longest path.
Okay, I mean that means when we are mentioning it as route, so we have to take that route for which route we are finding the maximum length.
Longest path, correct. That's the reason we are taking as a formula also maximum of that with this age or that age.
Okay.
Yes, ma'am.
Okay. So now is it clear? Who just made the comment?
Yeah, ma'am. It's clear for me. I mean, I just put this observation to
I
everyone.
guess to make it
Yes,
more
yes.
clear, from wherever it can come, we need to create a graph where the degree of an element is greater than 1. It generates the longest graph rather than the 0 degree.
Yeah.
Degree.
Like
Then it will be more clear.
we can think it like that. We can, like, if we have in degree 0, so we can take them in a single row. Okay, so we are finding the distance, the longest distance from that row only, right?
Yes,
We can
correct.
you can think this sort of thing in that way. So we want to find the longest distance from the whole row, not from a single vertex, right? So if I want to find the longest distance, then we have to take the maximum distance from considering all the vertices in the particular row with in degree 0, right? Which considered the all the vertices with in degree 0. So we can view the problem in such a way also, right? Am I right?
Yeah.
You're
Right,
right,
ma'am.
Trace.
Yes, ma'am.
Okay, thank you so much to pointed that out. You are also clearing my concepts.
Yes, ma'am.
No problem.
Okay, so next we have a new concept called transitive closure. Okay. So transitive closure of a relation. Okay. So we know what a relation is, right? Suppose we have a relation which is not a transitive relation. Okay. Okay. So we know what a transitive relation is, right? So transitive relation means if we have AB, comma BC belongs to the set R, then it will automatically imply that A, comma C will be in the set R, right? So this is the definition for transitive relation. So if we have a relation which is not a transitive relation, for this type of relation, if we consider a set, just let us denote it with R plus, containing the relation R. So relation is a subset of the set, right? If we define a relation on S, then it is basically a subset of the set S cross S, right? That we all know. So if we consider a superset of the relation, that means superset means which contains the relation, and this new relation R plus, this is transitive. So transitive closure, if just left the definition, if I just overview the what is the concept of
Can you please repeat this concept, ma'am?
Yeah, I'm repeating it. So if we just overview the concept of transitive closure, so that is basically if we have a relation which is not a transitive relation, for that type of relation we can define a particular relation which will contain the relation and which will be transitive. Okay. Once again, I am repeating, transitive closure of a relation is a relation. Like suppose if we have a given relation which is not transitive, then transitive closure of the relation is a relation which contains the given relation and which is transitive. Okay, that means we can define a new relation based on the previous relation. Okay, So just for example, we can understand this concept via example. So if we take R as the parent relation, that means A comma B will be in the set R if and only if A is parent of B. Okay. Suppose this is our relation. So clearly this relation is not a transitive relation, right? Can any one of you can unmute yourself and explain why the relation is not transitive?
Because if A is parent of B and B is parent of C, it doesn't necessarily say that A is parent of C. That
Like
is
not
not.
necessarily, no. It's obvious.
Yeah.
No? A is not a parent of C, but A is
Yeah, that's
ancestor
all.
of C, right?
Yeah,
So it
correct,
will
correct.
definitely imply A comma C doesn't belongs to R. Right? Even it is like a statement. A comma C doesn't belongs to R. So then
That is
yeah. So this is a example. We can just consider this type of relation, which is a relation but not a transitive relation, right?
Ma'am, a quick question. So this is not a transitive relation.
Mm-hmm.
Okay, yeah, go ahead and then I'll ask it. No, go ahead, finish that entire thing.
Okay. So as I said, we can define transitive closure for a relation which is not transitive. So now we have a relation which is not transitive. So obviously we can define a transitive closure R plus. And we define the transitive relation R plus with ancestor relation. Okay. I'm writing it shortly as A relation. That means A comma B will be in R plus if A is ancestor of B, right? That means there exists in mathematical way, we can write it such a way, R1, Rn, such that one. Okay. That means A plus relation is, we will call the relation as ancestor relation, and ancestor, like from the name it is clear that whenever A and B is in the set R plus, that means A is the ancestor of B, right? That means there are some person which are like in between A and B. That means we have some a sequence like that, such that A equals to R naught, and for each I belongs to this, that means for each I in this sequence we will have this belongs to R. That means our Ri is a parent of Ri plus 1, right? This is a member of the parent relation. That means Ri is the parent of Ri plus 1, and our B equals to Rn. Okay. That means the last point of the sequence is B, the first point of the sequence is A, and the middle points are like, we can choose the middle point like that. Okay, so this is the definition, and this is the usual, I mean general definition. That means if we have a relation which is not a transitive relation, then with the help of this definition we can always create a relation which is a transitive closure of the given relation. Okay, is the definition
Ma'am,
clear?
a quick question.
Mm-hmm.
Do you really mean to write A comma B, or did you mean to write A comma C? Because A comma B was already a part of the relation that you
No.
mentioned.
I mean, I am taking a random A comma B, not this particular A comma B.
Okay. Okay. So, but
This
in
is a
that
new variable. Just take
okay,
it as a variable.
okay. But in the case where you explained that A comma B and B comma C is present, but A comma C is not present, in that scenario, the relation that will be established that should be a part of R plus would be A comma C, right? Where we are establishing an ancestral relationship between these
Yes.
two, right?
Yeah. So
Okay.
because R plus is transitive, I mean, obviously, if A comma B is and B comma C belongs to R plus, that means A is ancestor of B and B is ancestor of C. So obviously, it will automatically imply A will be ancestor of C, right? Right? Then
Correct.
AC will be in the set R plus, right?
Symmetric, ma'am.
No, this is called transitive. This is a definition for transitive relation.
Okay.
Why do we ever need such transitive closure, ma'am? What's the need? What's the need for transitive closure?
Okay, so in the upcoming process, we will again calculate some like this type of thing, that means longest path or shortest path. So to calculate this type of thing, we need the transitive closure. Okay, that is why we are introducing this thing. Okay.
Okay. Okay.
Is it?
Ma'am,
Yes.
ma'am, can you repeat just these 3 points again? What is the exact definition? So you are saying if it's if it is not transitive, then there should be a R plus, and these 3 points should satisfy for transitive closure to happen, right? This is
Yeah. I mean, if you have a relation which is not transitive, then we can define another relation which contains the given relation. That means the given relation will be a subset of the new relation, and the new relation will be transitive. Okay. And the way we can define the new relation is this way. Okay, clearly when we are defining the new relation R plus, we are taking help of the relation R, right? In the second step, right? Clearly we are taking the relation R, and when A is a parent of B, that means A is basically ancestor of B, right? So again, when A comma B belongs to R, it will automatically belongs to R plus, right? So basically we have R is subset of R plus, and we can define R plus with the help of the given relation R. Then we can check that R plus is a transitive. Okay, that is the reason why we call this as a transitive closure. Okay.
Ma'am, could you give an example, ma'am?
Yeah, this was an example, right? I mean, if I take
Like between numbers, could you?
Between numbers. Okay, let me try. I didn't think about it. Okay, so suppose if we have S1, 2, 3. Okay, if we take R with just I'm taking the simplest example. Okay, so we took S as 1, 2, 3 and R as 1, 2 and 2, 3. So clearly 1, 3 is not there. That means our R is not a transitive relation, right? So clearly, if I just want to denote, so if I take this, just we are adding the point which I need, right? So this is the transitive closure. I mean, this is clearly transitive, and this is a superset of the given relation. Okay, is it fine?
This is not transitive relation. 1 to 2, 1 to 3, and 2 to 3.
Why?
Excuse me, ma'am.
Why?
Ma'am, it's a
Because of
transitive relation.
relation A to B and B to C and A to C.
So do you have any example? I mean, in this 3 point, do you have any example?
No, anything.
I mean, we have 1, 2, and 2, 3, right? That means we want 1, 3 in our set, and 1, 3 is in our set. But we cannot find any other combination, na? So that we can contradict the definition of transitive. Yes. Right?
Yes, ma'am, right.
So this become now transitive, right? If we add this 1 point, then this become transitive now.
Yes, ma'am. Could you explain the difference between transitive and transitive closure?
So transitive closure is like, transitive is a property, right? I mean, transitive closure is a set which contains the previous set and which is transitive. And transitiveness means it's a property, right? That means which satisfies this definition, right? A, B, B, C implies AC, right?
Hello, ma'am.
Yeah.
Ma'am, actually, I have asked one doubt in starting of this lecture. You have told me you will discuss after the class end. I have some doubt in activity 10.7.
Okay, so we cannot discuss it right now. We will try to discuss after the class, because we are now just discussing the summary of week 11, right? So in between the class, we cannot go to week 11 to week 3 directly, week 10 directly. And so, okay, so if we have the time, then we will discuss this after the class. Okay.
Okay.
So is the definition now clear?
Ma'am, like I'm not able to connect, ma'am. Transitive closure. The meaning of I'm not able to make it clear.
I mean, this is basically just take, if I have a relation, not transitive relation, then we can define a relation. I mean, define another relation, then relation containing another better mention transitive here. Okay, let me write it as T relation, that means transitive relation containing the relation R. This is the definition. Now is it clear? I mean, if you have a relation, not a transitive relation, then we can use the set, use the R, and we can define a superset of the R, which is transitive. This is called the transitive closure.
Okay, yeah, I'm able to make some meaning out of it.
Yeah.
I'll try and reach you later if there is.
Okay.
Yeah, please continue.
The thing is, actually, what makes make the set as transitive if we add any element. That's what transitive closure.
Yeah.
If you are containing the set which is not transitive, what makes that set as transitive? Which element to be added? So that is the reason this R plus, that's a superset is.
Ma'am, so can we say by adding 1, 3, it becomes transitive closure?
Yeah.
Yes.
And
yes.
it contains the previous set. I mean, it's basically, if we have a relation and which is not a transitive, that means some of the element are missing from the set, right? That means if we add,
to make this transitive, if we need to add something.
So if just add something to the set, it will become transitive. I mean, you can also extract something to become like, to make a transitive set, but it will be a subset of the given relation, right? But we want a superset. So we will add some element so that the given relation become a transitive relation.
Transitive relation.
And when
That's called as transitive closure.
And when we're adding the new elements, we will create a collection, and the collection is called basically transitive closure. Now, are you getting the concept?
Yes, ma'am.
Okay. Okay. So the reason why we always why we introduce the concept of transitive closure, because we know the adjacency matrix, right? And we will we will calculate the the transitive closure for our adjacency matrix also, with using the same type of concept. That means with the relation, like we can relate the relation with a graph, okay, with a directed graph, not a graph. Okay, so then we can relate the transitive closure of a relation to the transitive closure of the adjacency matrix for a graph. Okay, so let us just check how can we relate a relation with a graph, right? So if we have a directed graph, that means something like that. um, uh, Not this. Okay, just for example, let us take this is a directed graph, right? So if I compute the set of all edges, then we will get this, right? This, that means 1 to 2 is a edge, 2 to 3 is a edge, 3 to 4 is a edge, and 1 to 4 is another edge, right? So if I take the set E, and we can relate the set E with a relation, right? So again, if I take the set of all vertices as our mother set, so this E is nothing but subset of V cross V, right? So again, we know that if we have a mother set, then we can define, if we have the set A, we can define the relation A, which is nothing but subset of A cross A, right? So here we replace A by V and R by E. Okay, so the same concept we can apply for graph also. So we know the concept of transitive closure for the relation, right? That means R plus, and we know how to calculate the adjacency matrix for a given graph, right? And using this, we can also calculate the adjacency matrix for the transitive closure for the adjacency matrix, right? Which is basically nothing but same as the transitive closure of the relation. Okay, if I take the relation as E. Okay, this is the reason why we use the concept of transitive closure. Okay, and we want to calculate the transitive closure because again, I just told you, we want to use this concept in some algorithm, okay, to find some shortest path or this type of thing. Okay, so again, we had another definition for this, which is like 1 minus path of length greater equals to 1. Okay, now if I take I comma j here, that means the edge which is going from I to j, then we have to again take I comma j here also, right? That means the matrix, the ijth entry of the matrix will be exactly this quantity. I mean 1 minus path of all length, which is from I to j, which is greater equals to 1. Okay. So this is the definition, and that is why we just use this type of thing. Then we learn about AL, where this L basically varies from 0 to n minus 1. Okay. And what is AL? So we can we have another definition for AL. So in general, we can use the definition this means like if j this is equals to 1, if okay, So this is the general definition for AL. That means this is the notion of AL. But also we know the matrix multiplication, right? So once we have the matrix, this is the matrix, right? A, the adjacency matrix. So we can multiply A with A to find A square, then A with A square to find A cube, and so on. Okay. So this is a theoretical definition, but also if I want to find AL, we will just apply the matrix multiplication, then we can find the matrix AL. Okay, for all n belongs to the set. Okay, and the transitive closure is nothing but A naught plus A1, up to AN. Okay. This is a transitive closure, which is basically equals to our R plus. Okay. So this is the definition. Okay. So we have up to now what we learned. We learned how to calculate the longest path. Then we learned about transitive closure. Then we learned how can we relate relation with directed graph. And then we learned we can just extend the concept transitive closure of a relation to the transitive closure of a matrix, particularly the adjacency matrix, right? Now we have a new thing, just weighted graph. Okay. So what a weighted graph is? Now, like if we have a graph, weighted graph means simply it is clear from the name also. That means we will put some weight, right? And the weight can represent anything. I mean, weight is basically a representative. Like if I take the vertices, suppose some 1, 2, 3. This is suppose our tag. Okay. So this is the normal tag, right? Now, if I just add some number here, just some 10, 15 or 12, this now become a weighted graph. Okay. So clearly we just put some weight here over the edges, and these weights are basically representative of something. Like it can be cost, it can be distance, it can be time, it can be anything. I mean, if you are like analyzing some real life problem, suppose 1, 2 and 3, these 3 are representing some another cities like some Chennai, Bangalore or Mumbai. Suppose these 3 vertices are different cities. Okay. And the edges are the roots connected, which are connecting these 2 cities. Okay. So when we are putting the weight over it, so we can like express through the weight, we can express the length of the route, or we can express the time to cover the route. Okay. So weight is basically a representative. That's why I mean, to solve some real life problem, we need the weighted graph. Okay. And the weighted graph means we will associate weight with a given graph. Okay. This is called weighted graph. Okay. So for weighted graph also we have a problem to finding the shortest path. Okay. So this is our problem. Okay. So that means if suppose you want to go from Mumbai to Chennai. Okay. So that means in that way, suppose you want to follow the route which can take the minimum time, right? Which can take the minimum time to reach from Mumbai to Chennai. In that case, for this type of problem, reference problem, we have to use this type of formula. Okay. So you can find the shortest path. So whenever we know what a shortest path is, whenever we have a general graph, like with the shortest path, what we mean, the path which contains or which includes the least number of edges, right? So if I talk about, like, suppose if we have this graph without the weight, then what will be the shortest path? Anyone? From 1 to 3. 1 to 3.
Only 1, 2, 3 is the shortest path.
Yeah, this is the shortest path, right? But if I put weight here, okay, suppose this is our new weight, okay, then the shortest path will be in term of the weight. That means we will consider the shortest path as the path which will contain the least weight, okay? That means the path minimum weight, okay? So if this was the graph without any weight, then this was the shortest path from 1 to 3, right? But once we have the weight here, then we will consider the path which contains the least weight, okay? That means we will consider each edge, then we will consider each weight and we will add them, okay? So clearly, if I go 1 to 2, then 2 to 3, so we have the weight 1 plus 2, that means 3, right? And if I go directly from 1 to 3, so we will have 20. So clearly 3 is the least, right? So in case of weighted graph, we will take the path 1 to 2, then 2 to 3, okay? So this is the difference between normal graph and weighted graph, okay? In case of normal graph, we consider the shortest path which have the least number of edges. And for the cases of weighted graph, we will consider the path as shortest path, which has the least weight, okay? Is it clear? I mean the shortest path for a weighted graph. Is the concept
Yes, ma'am.
clear? Okay. Okay. So whenever we have a graph, then we know we can compute the adjacency matrix, right? And for a normal directed graph or any graph, what was the adjacency matrix? Whenever we have a edge from some I to some j, then we used to add 1, right? For that, like ijth entry, I mean the ijth entry was 1 if there was some vertex from I to j, right? This was the usual way to calculate the adjacency matrix in the case of normal graph. But if we have the weighted graph, instead of 1, we will put the weight, okay? So whenever we will have an edge like that, again we will have a weight associated to the edge, right? So instead of 1, we will just put the weight here, and this will be the adjacency matrix for weighted graph, okay?
So from 1 to 2, the adjacency weight matrix in weighted graph would be 1 over there, and 2 to 3 it would be 2, and
Yes.
1 to 3 it would be 20.
Okay.
Am I right?
Yeah, you are right. So let us just calculate the adjacency matrix for this graph, okay? Okay. So what is 0? Sorry, it will be 1, 2, and 3, right? So what is 1 to 1?
0.
What is 1 to 2? 1, right? 1
Yes,
to
ma'am.
2. That means this edge. 1 to 3?
20.
Right. 2, 1?
0.
0.
Yeah. 2, 2, 0, right? 2, 3.
2.
Correct. Okay. 3, 1.
0.
3, 2.
0.
And 3, 3 will be again 0. Right? So this is the way how we can calculate the adjacency matrix for a weighted graph. Just instead of 1, we will put the weight which is associated to the particular edge. Okay. Is it clear up to now what I covered? Is it clear to all of you?
Ma'am, just a question here. So you're saying the path which has the minimum weight should be chosen here, right?
Yes.
So for 1, 2, 3, it's 20. So what will be the final solution for this? What is the minimum path with the minimum weight?
This path. This is the final solution. 1 to 2 and then 2 to 3. So if I go, if I want to reach from 1 to 3, then we have only 2 options, right? We can directly go from 1 to 3 and we can go from 1 to 2 and then 2 to 3, right? So if I go from 1 to 3, then the respective weight will be 20, right? And if I go through this path, that means 1 to 2 and then 2 to 3, then the respective weight will be 1 plus 2. That means 3, right? So clearly the least weight is 3. And this is associated to the path 1 to 2, then 2 to 3, right? So for the weighted graph, we will consider the path 1 to 2 and 2 to 3 because this path has the least weight. Okay.
Oh, okay, ma'am. Got it. Thank you.
Okay. So
One doubt, ma'am.
yeah.
Ma'am, 2 to 1, how could it be 0? Like 2 to 1, there is no part. So it should be infinity, na?
Yeah.
Yes. In 3 to 1, it should also be infinity.
So what was the adjacency matrix? Just wait. I guess if there is no part, there should be 0, right? Someone of you can just guide me. What was the definition of adjacency matrix? Can you just recall it?
Ma'am, may I know why it is coming infinity?
Yeah, that is what I am asking. What was the definition for adjacency matrix?
Okay. So if it is adjacency matrix, so but in Bellman's-Ford algorithm, if we count the shortest path.
No, not for the shortest path. Like how can we calculate the adjacency matrix for a given graph? So as I remember, the definition was like the ith entry will be 1 if there is a path from I to j, right?
Yes, ma'am. I think you are calculating the shortest path. Okay.
Yeah, no, not the shortest path. I'm saying about the adjacency matrix. So if I have a given graph, then we can compute the adjacency matrix via this definition, right? And other entries will be 0, right? This was the definition for adjacency matrix. Right?
Yes.
So here the definition is same. Just instead of 1, we will put the weight. Okay. So we will not use infinity for adjacency matrix. So we will use 0 here. Okay.
Yes. But you are putting 1 and 2, so I think you are calculating that algorithm shortest path. So that's
no. This is the adjacency matrix for weighted graph.
Okay. So
is it visible? I mean, I guess it's too small. Can you see this?
yes, ma'am. Completely.
Yeah. Okay. So this is not the way to find the shortest path. This is the way how can we calculate the adjacency matrix for weighted graph. Okay. That means this is, we have just simple definition. For weighted graph, for normal graph, we calculate the adjacency matrix like whenever we had a vertex, whenever we had a edge from the vertex I to j, we used to take the element, the ijth entry of the matrix as 1, right? Here, instead of 1, we will put the respective weight. That means the weight which is associated to the particular edge. Okay. So this is the definition between the adjacency matrix for normal graph and the adjacency matrix for weighted graph. Okay. Is it now clear?
Yes, ma'am.
Okay. So all of you are okay with this concept, right? Up to now. Then we can move next.
Yes, ma'am.
Okay. Very good. So whenever we are talking about weight, so we automatically have two different options, right? One is positive weight, another is negative weight, right? As I said, whenever we are putting weight over a edge, then the weight is like representing something, right? So it depends on the way how we are representing the graph. What is the weight meaning? Okay, so depending on the meaning, the weight can be positive or negative too. Okay, so if we have the weight as some negative number, then obviously it is a negative edge weight. Okay, and what a negative cycle is, then we have a new term called negative cycle. So negative cycle means, suppose we have a cycle, we will take the same example again, 1, 2, 3, like that, 4. So this is suppose our cycle. Okay. So if I want to calculate the weight, okay, so suppose this is the weighted cycle. Okay, that means this is the cycle associated with the weight. Okay, so suppose I want to calculate the weight for the cycle, that means we will calculate the weight, like we will calculate the weight of each edge and we will sum them with one round, right? That means the weight of the cycle will be 1 plus 2 plus 1 plus 1. Okay, that means 5. This is how we can calculate the weight of a cycle. And negative cycle means clearly the weight will be negative. Okay, if the weight of a cycle is negative, then we say that the cycle is a negative cycle. Okay, suppose we have -1, 2, -4, 1. Okay, then what is the weight of the graph? Clearly this is -2, right? That means we have a negative weight for the cycle 1, 2, 3, 4.
Ma'am, may I know, if the total weight is coming positive, but there is a negative weighted graph in one, like from 1 to 2, it is -1. From 3 to 4, if it is +4, then would it be called as negative graph, or because the total answer would be in positive, right?
No, like we will concentrate over the total answer. If the total answer is positive, then this is not a negative graph. If the total answer is negative, then only we will say this as a negative graph. Okay. So here also you can see that we sum of all the weight, right? -1 plus 1, -4 plus 2. Then we got the total answer as -2. This is negative because so we are we are saying the graph, the cycle as a negative cycle. Okay, so if the total answer is not a negative number, then we cannot say the cycle as negative cycle. Okay.
Okay, ma'am.
Ma'am, a question. So when we started with this weighted graph, then you immediately gave an example that let's say if we have to travel from one city to the other, then let's calculate which one takes the minimum time. So
Yeah.
there, the application of this weight makes sense, right? Where can you give me an example where a negative weight would make a sense? Like, where exactly it would be applied?
Okay. So if I just take it in a negative way, I mean, if I suppose, let me just think, if just suppose we have a place A, then we have a place B, okay, we have a place C, and suppose this type of graph we have, and suppose we are associating the weight with the like suppose we want to reach from A to B, okay, this is our goal, to reach from A to B, and our target time is to reach from A to B is just for convenience, suppose T, okay, this is our target time. That means suppose we have a target that in time T we have to reach from the city A to B, okay. So for this we have this route, one can go via A to C, then C to B. Like this is a route A to B. Directly we can go A to B, and directly then we can choose this way too. That means A to C, then C to B. Okay. So these two way we have. Okay. So suppose if I associate the weight, the extra time, I mean, weight means the extra time. Okay, let us associate the weight as the extra time taken. Okay, so if I put something positive here, that means we need the time to reach from A to B T plus 1. Okay, that means the extra time taken is 1. That means let us assume the unit is same for all the timing. Okay, so the whole time, the total time to reach from A to B is T plus 1 then, right? And suppose here we have something negative and something, maybe something positive. Okay, here, I mean, then here we have, in this way, I mean, from A to C and C to B, we have the total weight as -1, right? Then if I follow this way, then the total time be T minus 1, right? So
I mean, I did not
-2, okay. Whenever I'm like taking -2, that means I mean ki, I need the time 2 lesser than the time T to cover this distance. Are you getting the point?
Okay. So your unit of time is like absolute time. Like let's say if you are taking 20 minutes,
Unit
then
is
you're saying that.
absolute.
Oh, okay.
But T, suppose just T is fixed. Whenever we are putting 1, that means we want extra 1 minute. And whenever we are putting -2, that means we want 2 minutes lesser than the time T. Okay.
Understood. Thank you.
Okay. So is it clear? The example is clear for all of you? Like how, why we introduce the concept of negative cycle? Why do we need it?
Just I got lost connection. Just can you brief it with a line or one word? Yeah.
Sure. He just asked for an example in which we can like use the negative weight. Like why do we need to introduce the negative weight even? How can we use or introduce the negative weight in a practical sense? Okay, so I just explain the example. Like if I have 3 cities A, B and C, okay, and suppose we have a time T, okay, so when we are associating 1 over the edge AB, that means I want 1 minute extra, that means 1 unit extra time than T, that means total time is T plus 1. Okay, and whenever I am associating -2 here, that means I want we need 2 minute or 2 unit less time, lesser than 2 minute or 2 unit lesser than t. That means t minus 2. Okay. So
Yes.
here I took wait as extra time taken. Okay. That means extra time than t. So whenever the extra time is 1, so total time is t minus 1, right? And when the extra time is minus 2, that means the total time will be t minus 2, right?
Yes.
Yeah. So that is how we can find so many examples, so that we can use the negative way, so the like to solve some practical example. Okay, so is it clear?
What is the real-time example?
This is the real life example now, what I just told you. Like if I want to reach from the city A to B, so which way should I choose to reach from the city A to B in a minimum time? Okay, and I just took wait as extra time taken, and I have a time t, and then I just described how can we example like use the negative weight. Okay,
-2, it is -1 minute you are reaching to the city, right? -1 is not time or whatever we cannot say.
no, minus 1 and -2, these all are wait, right? So wait means extra time taken. So whenever I am assigning -2 over some age, that means I need 2 minutes less than the time t. That means I need the time t minus 2 to reach from A to C.
Yes. Yeah.
Okay, got it?
Got it. So extra time. So already 2 minutes is taking. So -1 minute. So 3 minutes extra. I mean 1 minute extra. So 3 minutes.
Because we have -2, that means we are not taking like something greater than t. We are taking less time than t. Here we have positive, that means we are taking extra, I mean greater time than t, right? Here because you have negative, that means we are taking lesser time than t, right?
Yes, got it.
Okay. So the example is clear to all of you? Is it clear?
Yes.
Yeah, we can move.
Okay, so now you just got the idea about weighted graph, negative weighted graph, and negative cycle. So immediately we have a remark. So because our next problem is finding the shortest path. Okay, so we will work on the problem finding the shortest path. Okay. So just note the remark. Once we have a negative cycle in the graph, then we cannot find a shortest path. That means a shortest path is not defined in that case. I will explain why. So just let me write the remark first. Sorry. Okay. So this is the remark. So I will definitely explain why the remark is true. But before that, is there anyone who can just give a brief idea why is it true? Once we have a negative cycle, then maybe for some vertex, we cannot find the shortest path. Someone can briefly give the idea. Any idea? If you have a rough idea, just unmute yourself and tell me the rough idea. Then I will describe why is it the case.
So you're asking that if there's a negative, then we cannot really find the shortest path using that, right? That's where.
Just repeat once again.
Ma'am, you are asking this question, right? Why is this the case that a negative cannot be used for?
Yeah, like if I have a negative cycle, we know what a negative cycle is, right? So if I have a negative cycle in our graph, then we cannot define a shortest path. So what is the reason?
Perhaps the reason being like when we calculate basically when we calculate the number of levels at that point in time, we assume things to be like see, the shortest path is what I remember is using a BFS. Now in the BFS,
No. Here, whenever I am saying, like whenever I will use the term shortest path, because we are now moved to weighted graph, so we will use the new terms. Okay, so shortest path means the path containing the least weight. Okay, so we will not use BSF here. Okay, BFSF.
yeah, so then the negative does not make sense at all, right? Like if we will, then we literally cannot calculate using that, because 1 and -1, if we do it, then it essentially gives you the 0, but it's a false perception that you're getting. You're still traveling 2 nodes and you're saying that it's a 0, it's a false perception. So
No. It's not a false, because yeah, when you are going 0 and when you are going -1 and then you are going 1, then you are fine. If you are finding 0, then it's perfectly all right. So we don't have any problem with 0. I mean, there can be 2 point because weight is not
Ma'am,
defined.
because
Yes.
like negative weight cycle, the shortest paths keep decreasing endlessly, so it can't be
Yeah.
defined.
Right. Very good. I just wanted to listen this thing. So I will explain this. So
Ma'am, what did he say? Could you repeat?
yeah. I will just explain his word right now. Suppose we have the graph, okay? Suppose this is our graph and we will just let us assign some weight random. So just for okay, suppose this is our weighted graph, okay, and we want to reach from 1 to 5, okay. So one way we can go this way, right? That means 1 to 2, then 2 to 5, right? So in that case, what is our weight? This is 2 plus 2 equals to 4, right? So as I told, whenever we are calculating shortest path in the weighted graph, we will consider the path containing the least weight, okay? So we have another way, because we have a cycle here, so we can consider this path to 1 to 2, then 2 to 3, then 3 to 4, then 4 to 2, then 2 to 5. This is another way, right? And what will be the associated weight? This is 2 plus -6. We are going this way, right? Plus 1, plus 2, then plus 2, right? So this become 1, right? So clearly 1 is the less. But if I just round it twice, I mean like that. That means 1, 2, 3, 4, 2. Then again, suppose we round it once again. Okay. So this is also again a possible way to reach from 1 to 5, right? And obviously, what is the weight of this path? This will be 2 minus 6 plus 1 plus 2 minus 6 plus 1 plus 2 plus 2, right? Right? So what is the graph? I mean, what is the total? 2 plus 2, 4, 6. So 6 and 6 will be cancelled out. 2, 4. That means -2, right? Again we have -2, which is the smallest. So again, if I round the cycle once again, then we will get again one number which is smaller than the number minus 2, right? So in that case, we can round the cycle infinite time. So we cannot define the exact smallest weight or exact least weight in that way. Are you getting my point?
Yes, ma'am.
Yes, ma'am.
Yeah. So that is why if I have a negative cycle in the graph, we can round the cycle infinite time, and whenever we will add one more round towards the cycle, we will get a lesser weight, right? So we can never define a least weight, right? The path containing least weight. Okay, that is the reason why for a graph which contains a negative cycle we cannot define the shortest path. Okay, this is the remark. So now let us move to the problem finding the shortest path. Okay, so this was our main focus, main goal. So when we have a weighted graph, our problem shifted towards the finding shortest path. Okay. Here we have two different ways. That means we can view the problem in two different ways. First is single source shortest path. Okay. Okay, and the second thing is all pair shortest path. Okay. So again, it is clear from the name itself. So single source shortest path means we will first fix a vertex, then we will find the shortest path from the fixed vertex to some another vertex, right? That means our starting point is fixed here, and ending point we can vary accordingly. And all pair shortest path means we will find the distance, the shortest path between all the pairs, all the vertices. Okay. Okay, so these are the two ways we can deal the problem with. So first we will deal with the single source shortest path. Okay. Okay. So we have two different rules, two rules to solve this problem. I mean, if I fix the starting point, then we can vary the end point accordingly, accordingly to the question. Okay. So how can we find the single source shortest path? So the first algorithm which we will learn is called Dijkstra's algorithm. Okay. Dijkstra's algorithm. Okay. So what the algorithm says, whenever you will have a vertex, you just first you have to fix the root, right? Like from which point you want to calculate the shortest path of the other vertices. So first you have to fix the source. Okay, this is the first step. Okay, once you have fixed the source, then we can proceed with the algorithm. And what is the procedure? That in the next step we have to choose another vertex which is connected to the source having the least weight. Okay. And then step 3 is like we will continue this process until we can cover all the vertices. Okay, that means we will continue the process up to the end. So this is the procedure, this is the discards algorithm, how we can just calculate this type of thing. And the procedure is we will list the vertices, we will list the distance, and then we will note the previous vertices. That means from which vertex we are calculating the distance to the new vertex. Okay, so this is the way, this is the way how we will proceed with the discards algorithm, and this is the algorithm. That means this is the particular process. Okay, so let us understand with a particular example. So if we have the graph, okay, suppose this is our graph, which is a weighted graph. Okay, suppose this is our weighted graph, and we want to find the shortest path from a vertex. Okay, so first we will follow the steps. What is our step 1? We will fix the source. Okay, so the step 1, we will fix the source, or let us take the source as 0, and then obviously because 0 is the source, so the distance will be 0, right? So we will parallelly just create the list. So this is the vertex, this is the distance, and this is the previous vertex. Okay, so we have the source 0. Let us list out all the vertices. So we have 0, 1, 2. Am I audible, right?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
So if you are facing any problem, just unmute yourself and ask me. Okay, otherwise I will not be able to see the chat box. Okay, so we listed all the vertices. Okay, now we will proceed with our algorithm. So the
What is
first
the third column, ma'am? What's the third column that you have written?
Previous vertex.
Okay.
That means from the vertex which we are like considering the edge. Okay, like the edge associated to the weight. The weight associated to the edge. Okay.
Okay. List of edges or just the immediate edge?
No, just immediate edge. That is why we wrote it. We can write it as previous vertex, right? Just the immediate vertex, which is previous to the present vertex. Okay. So what our first step was to fix the source. So we have fixed the source. Once we have fixed the source, we will update the distance as 0. Okay, 0 distance from 0 to 0 is obviously 0. So the distance is 0. Okay, now we will check the second step, which is choose another vertex which is connected to the source and having the least weight. Okay, 2 point is important, connected to the source and having the list. Okay, so our source is 0 here. Okay, so we have only these 2 edges which are connected with the source, right? And the vertices 1 and 2, that means only these 2 vertices 1 and 2 are connected with 0. So we are done with the first portion of the second step. Now we have to choose the the edge which has the minimum weight, right? So which vertex shall I choose?
One.
Yes. So we will choose then 1, and the distance from 0 to 1 is 10. So we will write the distance and we will write the exact previous vertex. okay, which is 0. Now we move to 1, and the third step is we will continue the process. Okay, when we have arrived to the point, the vertex 1, then again we have two edges, which is connecting 1 with 2 and 4, right? And we have associated with it 2. So which one we will choose next to 1? So we have, yeah, we have 2 and 4. Then we have to choose accordingly to the respective to the weight, right? So we will choose 2 because 2, this edge connecting 2 and 1 has the least weight, right? So the distance is 6 and the previous vertex will be 1 for 2, right? Then we have 2 and we have two options. One is connecting 2 with 0. So for 0, we are already done. So we will not consider 0. So we will go to the point 3, right? So we will update the weight, the distance and the previous vertex for 3, which is 70 and okay, sorry. It will be not 6, it is 16, because we are finding the distance from 0 to the respective vertex. So when
we need to add them also,
we
right? You
need
wanted
to
to
add them, yeah. So we have to add 6 plus 10, so this will be 16. Then we have to add this 2, right? So this will be 86, right?
Actually from 1 to you have to go to 4, right? Because that is the less.
Why? This is 20, no?
Between 4 and 2, if we compare, it's 6, right? But if we add in overall, if we check, then what Ilanga sir is telling, it's correct.
Wait,
It is like 2 to 3. You just went to 2 to 3 directly. But
okay,
however,
because
we have 1 to 4 supposed to go, right?
No. See, whenever I have like when I am at 1, then I have these 2. Okay, so these 2 option. Okay, now I have to choose one option between these 2. Okay,
That
so
is fine.
from,
That is fine.
yeah. So from these 2 we have choose 2, right? Now we arrived at 2. Okay, then we have to consider these 2 edges only. So this is not in our option when we are at 2. So what is the second step? We have to choose another vertex which is connected to the vertex. I mean, to the source, means now the source, not the source.
1 also the source, right?
Yeah, but one is, I mean, whenever we arrive to 2, then we will work with the vertex 2. Whenever we have to do something with 2, until that we cannot move to the vertex 1. Okay, until that we have to first finish finish all the work with 2. Then if we don't have any option to go further, then we have to arrive to the previous vertex from where we can again move. Okay.
Ma'am, just a question. If we have to find the shortest path between 0 to 5,
0 to 5. Okay.
Yeah. And since the weight from 1 to 2 is 6, then we will then that will not be the shortest path, right? Since the weight is less, we are going to that path, but the shortest path will be the straight path, right?
No, because we are using weighted graph. So for weighted graph, what do we mean by a shortest path? The path which contains the minimum weight, right?
Okay, so we will go from 0, 1, 2, then probably since he is not connected
0,
to anything.
0, 1, then 4, then 6, then 5. If I want to find the distance from 0 to 5.
Okay, so we will go to 0 to 1 to 4, then 6, then 5. Okay,
Yes.
that makes sense. Okay, thank you.
Okay, so the process is like what I was explaining. The process is like when I am at 1, then I have the this 3 options. That means the edges which are connected to 1. Okay, so after this step, when I already choose the point 2, then we can only consider the edges which are connected to the point 2. Okay, if I don't have any edge to choose, then I can back to 1, but whenever I have something to choose, I cannot back to 1. Are you getting my point?
Ma'am, can I ask a doubt over here? If there is the weight of edge between 1 and 2 is 16, will it go back to 0? Like from 1 to 0, will it go back? Like if it is 6,
I didn't get your doubt.
if the weight between 1 and 2 is 16.
1 and 2.
Yes, 1 and 2 is 16. We have come from 0 to 1. If we check for 1 around 1, then
we are no. See, here we are calculating the distance from 0 to each of the vertex. So all the distance which is mentioned here is from 0. Our source is 0 here. So the 16, I mean, for 2, I wrote the distance as 16, which is the distance from 0 to 2. I mean, we will go from 0 to 1, then 1 to 2. So it will be 16. And this is clearly this is the least weight, right? It was your doubt or not? I mean, is this what you were saying? Hello? Am I audible?
Yes, ma'am.
My
Yes, ma'am.
network was bad.
One by one.
My network was bad. Could you just repeat what you said just now, like a while ago, after I spoke?
Okay. So because here what we are doing, we are doing this single source shortest path. That means we have a fixed source, and whenever we are finding the distance, that means this is the distance from the source itself. Okay, so whenever I mention 16 along with 2, that means this is a distance of 2 from the vertex 0. Okay, this is not a distance from 1. This is the distance from 0.
No, ma'am. I'm not adding. Like, no, I'm not telling 10 plus 6 is 16. I'm telling if 1 to 2 is only 16. Like if you add, then we'll get
that
26.
means you are saying this.
Yeah. If we come from 0 to 1, since 80 is greater than 10, so we choose 0 to 1. From 1, we check which is the shortest distance.
Yes.
Then we get to see 1 to 0, because it's not a directed edge. 1 to 0 is the shortest distance. Will we go back to 0?
Okay.
I'm asking.
No. We will not go back to 0, because once we covered the point, that means we are done with the point. That means we know the distance of the point from the vertex 0. Okay, so we cannot go back to, like, we cannot cover the same edge twice. Are you getting my point?
Got it, ma'am. Okay.
We can
Understood.
get back to the point, but we cannot cover the same edge. If I go back 1 to 0, then we have to cover this edge once again, right? This is not possible. Okay.
Okay,
ma'am, but that is only not possible if we have not explored all the children of that specific node, isn't it? Because with the logic that you just said, let's say if I were to find out the path between 0 to 5, in that case, I go from 0 to 1 first. So I say 10, and then from 1 to 2, I choose, because 10 plus 6 is less than 10 plus 20, correct? Right?
Yes.
And then from 2 to 3, and then from 2, I do have to come back to the 1, isn't it?
Yeah, but then at that time we will move to this way, right?
Exactly. That's what I'm saying.
We will cover this edge.
Correct.
Not
So
this or this.
A node is considered to be a visited node
yes,
only if all the children has been explored.
Yes.
Of the given node, right?
Yes,
Okay.
yes. That means all the vertices which are connected to the node. Yeah, you are right.
So, ma'am, in this case, the distance will be 0 to 1, then 2, then come back to 1 again, and then 4, and then
No,
6.
First 0 to 1, then 2, then 3. Because whenever we are at 2, then we have these 3 options. Okay. Like if we don't have any option, then we can come back to 1 and then we can move. But here we have an option, right? I mean, here we have an unexplored vertex. So first we have to explore the vertex, then only we can come to the previous vertex to explore further. Okay.
Okay, so 0, 1, 2, 3, and then back to 2, 1.
Then back to, yeah, not back to 2 directly, we will be back to 1. Then we will again move from 1. Okay. I mean,
but
we
3 and
will,
1 is not
we will,
connected.
what?
Yeah.
No, we will move via that, but we will not record the path in our list. Like we don't have to do anything for the path. We will go from 3 to 2, then 2 to 1. But for this process, we don't have anything, like we don't have to add anything in our list. That is what I am saying. Okay. Because for the vertex 2, we have already updated the distance. Okay. And for discards method, we update the list only one time. Okay. Once you updated the list, that means this is the final. This is the first and this is the final update. Okay. For this method. Am I clear?
Yeah, ma'am. Ma'am, can we run through like one complete example of like just one run with this algorithm?
Yeah.
Ma'am,
This is what
it's
we
a
are
small
doing now.
request. Could you make it tomorrow? Like for me, it's getting late.
Yeah, I will just cover this method, and rest of the method I will cover tomorrow. Just
Okay.
let us at least finish this one. So,
Yeah, so what we covered, ma'am, was from 0 to 3, right? That's what we covered right now.
Yeah,
Correct?
from 0 to 3. So we
And-
first go 0 to 1. Then
Yeah.
because 6 is list, so we will go 1 to 2. Then because we have only one option left, then we will choose this option. Then we updated the distance of 3, and this is the least distance or the shortest path from 0 to 3, which is 86, right?
Okay,
Then
okay.
because we don't have any other option here, right? So we will back to 1 via 2, because we will back to 2 first. Again, here again we don't have any other option, right? Because all the 3 we cannot consider any one of the 3 edges, right?
Correct. So let's just say that we say that the 2 is already visited now. Like
Yeah.
it's already done.
Yes, right, perfect. So 0 is visited, so 2 is already visited, 3 is already visited, so we have to come back to 1. Okay.
Ma'am, what is our destination, ma'am, actually? Like to find the shortest distance or
yeah,
from any vertex?
there is no destination. I mean, our target is to cover all the vertices, so that we can find the shortest distance from the source to all the vertices.
Okay.
Like we want to find the distance from 0 to all the vertices. Okay. And these are the respective vertices, and these are the respective distance from 0 to the particular vertex. Okay.
Yeah, got it.
Okay. So once we come back to 1, so then we will move to 4, because we don't have any other option, right? So then we have to move to 4. So once we come back to 1, and what was the previous vertex for 1, which is 0, right? So we will consider the edge 0, 1, and we will add this number with this number. Okay, so we will now get 30, and the previous vertex will be 1 here. Clear? And then 1 become a visited vertex, and then we have 4. Up to now it is clear, right?
Yeah, ma'am. It's clear.
Okay.
So when we come back to a node, we say what's the shortest distance to reach that specific node plus the direction forward.
Yeah.
What you
Plus
did,
the
right?
direction forward. Yeah. Then again, we have to repeat the same procedure, right? When we are at 4, that means we have these two options. These two options are only feasible option for us, right? So we have to choose one way, one option from these two options. So which one we will choose?
Let's say we can pick like anyone, right? We just pick anyone and we
No.
move forward. We need to
No.
choose the less one, right? 5.
Less. Yeah. So we have to choose 4, 6, 4, 6, 8, right? Right?
Yeah, correct, ma'am. 4, 6.
Yeah. So whenever we are moving for 4 to 6, we have to update the distance or the vertex 6, right? And what will be the distance? So we are moving from 4 to 6. So we will check the distance for 4. Then we will add the new distance, right? So this will be 35. And the previous vertex will be 4. Clear? So once we have at 4, we have only one option and we will go to the 5. And then we will check the distance 4 because the previous vertex is 4. Then we will add this new distance with the previous distance. It will be 45. Okay. So these are the all vertices. Now we have covered all the vertices. So we will stop our algorithm right now. And these are the vertices and these are the respective distance from the point 0 to the respective vertices. Okay. So if you have any doubt, you can ask.
Okay, now I get it, ma'am. From 0, we are calculating all the vertices distances.
Yes.
Is it the summary?
Yeah.
So we need to check for all the vertices. Okay, thank you, ma'am. Yeah.
So we are calculating the distance from 0 to all the vertices. Okay. So for
Okay, ma'am.
this,
So since the neighboring vertices for 1 was 2 and 4 and the lesser weight was of 2, we had to go to 2, otherwise for 0 to 5 we would have directly come to 0, 1, 4, 6, 5. So it's about weight that
it's about weight. So we have to choose the way, the age which has the minimum weight. Okay.
Got it, ma'am. Thank you.
So yeah, if you have any other doubt, you can ask. Then we cannot cover more topic right now. So in tomorrow's class, we will cover the rest of the topic and we will solve some of the problems. So,
Ma'am, may I know how much topic is left, like in percentage, like 60 to 70 is completed or not?
Okay, so I will mention the topic. So, so as I mentioned here, whenever we are trying to finding the shortest path, we have two different ways. First one is single source shortest path, and second is all pair shortest path. I mean, the second thing is we have to find the shortest path between all the vertices. So for single source shortest path, I covered one algorithm, and there is another algorithm. So we have to cover that algorithm. Then again, we have another algorithm called all pair shortest path. Then we have some other concept. So maybe 30% of the portion is left still. 30 to 35.
Oh, okay. Thank you, ma'am.
Yeah,
hello, ma'am. Actually, I have a doubt, ma'am. I have asking the start of the lecture in activity 10.7.
Can you take a screenshot and share it in the chat box?
Yeah, ma'am, I already shared there, but I am sending again.
Okay, so just I want to make sure anyone of you don't have any doubt with the topics which I covered, right?
No, ma'am, just a question.
I have some outstanding regarding that transitive closure, but I want to read more first before coming back.
Okay. Then if you are still getting like doubt, then you can ask in tomorrow's session.
Yeah, sure. I'll just solve some questions, maybe some read. That's it.
So Tuesday we will have the open session. Before that, try to solve questions so that the session can be more interactive.
Definitely. Thank you.
Welcome.
Yeah, ma'am, I have shared in.
Okay. So I guess you don't have any doubt with the week 11. So I just try to solve this one. Okay. So what is the problem? Okay. So we have a graph and okay, DF is performed from A such that when we visit a vertex, we explore its unvisited neighbor in alphabetical order. Which of the following options are correct? So the vertex. Okay. So we are exploring the unvisited neighbors in an alphabetic order. Means we are going from A to B, then B to C. Then we cannot go to C to D directly because we don't have any direct edge from C to D.
Yeah.
So we have to then
Go from C to F.
Yeah, we have to C to F and then F to D.
F to D.
Yeah.
So, ma'am, I have designed means write the same pattern there with their pre and post order number. And I have compared means pre and post order of C each this interval containing the pre and post order of this F interval. Then CF is a forward edge, na?
Okay.
Means, ma'am, I have also shared that screenshot in a chat portion.
Yeah, AC is a forward edge. So what is the problem here? AC is a forward edge, right? A then C, so it's a forward edge, right?
Means C and F is a forward edge, na? CF.
Ma'am, can I add over here? I understood his problem actually.
Okay.
Bro, first we have to draw the tree edges, then we need to go for non-tree edges, right?
Yeah.
From A, if you go, if you're intending to draw the tree edges,
Yeah.
then B will be coming in the alphabetical order.
Yeah.
So A, B, from B to C, and since C is not directly connected to D, so if we check, we'll come to F, from there F to D.
F to D.
This
Then
is the
it's
let me
the
complete.
order in DFS, na? Means depth for search.
Let me complete. So we have ordered this in tree edges.
Yeah.
Then we need to check for non-tree edges. So B to D is there. There is a connection from B to D where you can see we have not included that in our tree edge.
Yeah.
And A to C also we have not included.
Yeah.
Then we have to number that, and then for that, since it is a directed graph, there are three types of non-tree edges: forward edge, backward edge, and disjoint edges.
Disjoint edge.
So CF won't become a non-tree edge. So we won't even come under non-tree edges. I hope you understood.
It's asking about the forward. Means CF is a forward edge or not?
No, we should not we should not check the number. If you check the number, then you will get as CF as forward edge, but it's not a non-tree edge, right? I hope you understand. First preference is for non-tree edges.
Where it is given for non-tree edges?
You have to watch the lecture properly.
I have seen the lecture and seen the screenshot.
No, you have since you are in the debate, you have shared. See, it's yeah, ma'am.
It's talking about tree edges.
Am I wrong?
No, you just continue. I'm listening to you.
Like
yeah, I think what Manish is explaining is the right one. Like, that's how it is to be navigated.
Yeah. Yes. Yeah. So I guess you got the point, right?
No, ma'am. I have already shared this lecture, means screenshot, ma'am. This I have seen the lecture too. After seeing the lecture, I have completed this question. I have shared the screenshot in chat box.
Okay, then I will request you to just check the lecture, at least that particular portion once again.
Yeah, ma'am. I have shared you that the particular section screenshot in chat section.
Yeah, that is what I'm saying. You just recheck the lecture once again, then you just try to solve the problem once again. Okay, then if still you are facing the problem, then come to me, then we will solve. Okay.
Bro, see, in the lecture only you can see classifying non-tree edges and directed edge. You can see the side heading. Could you see?
Means
Yeah,
we need
it's
to determine it from a non-tree edges, whether it is a forward edge or back edge or cross edge.
uh, I hope you are confusing.
Yeah, that's why I'm saying ki,
Uh,
don't be confused. I mean, just check the part of the lecture once, then just try to solve the problem again.
Solve 1 second, brother. We are here. Tomorrow also you come again.
Actually, I have waited total 2 hours, ma'am, for this question because I have simply showing this because my city portion is
No.
backdated
Yeah.
math
Okay,
portion.
I can get your point, but he explained you na how to solve
Yeah,
this question, but
I
you are
have
not.
told you properly, brother.
Yeah, but you are not getting it. That means you didn't follow the lecture properly. That is what I'm saying. You can just follow the part of the at least that part of the lecture, then again revisit the problem so that you can at least get the explanation.
Okay. Thank you.
Thank you, ma'am.
Okay. So we can end the session right now. Let's meet tomorrow and just cover rest of the session, then solve some problems. Okay. Let's not.
TA sir, to provide the recording section, make the recording accessible. The recording class is not
TA
accessible.
class. Okay. We will do that. Okay. Okay. So yeah. Good night, everyone. We can
When is the session, ma'am? For you said some
same
open
time.
session there.
Okay. So I guess tomorrow we will not get that much time to cover the open session because for open session we need some time. So maybe we will solve with us problem and we will cover the rest of the concept tomorrow. Then a day after tomorrow, that means your Tuesday, we will cover the open session and I want you to solve the problem before the open session so that the session can be more interactive.
Okay, sure, ma'am. I do have one question, outstanding question that I was never able to understand. I'll just put it in the chat, like if someone is understanding that,
Yeah,
do
sure.
let me.
You do have a WhatsApp group, right? For discussion?
No, that WhatsApp group,
Yes.
that WhatsApp group, ma'am, I don't have. I'm just added to that. There is like one group in which all the session, like when the exams will be held, that is a part
Okay,
that
so
I'm aware.
you don't you have any discussion WhatsApp group?
No, there is one group in which just all those SCT sessions when the exams will be held, those part
Okay.
are actually coming up. But I don't have a group. If there is a group, if you could let me know, that would be great.
I guess you have some group. I mean, there are 9 other students. So if you know about some group or else you just inform him about it, then because only some of the students are there. So I don't think like it will be that much helpful for you to share the question here. Also, you can share the question here in the chat box, but if there is a WhatsApp group, you just share the question in the WhatsApp group.
Yeah, sure. Okay, all right, ma'am. If there is a WhatsApp group, I would love to join it.
Yeah,
because...
and you just share your question here also, so that I can also see the question.
Yeah, this one, ma'am, like whenever we come next time, if you could just help me understand this one, because I looked through a couple of articles on the internet as well, but this one I'm not able to really understand. There are some, few points around it, but I'm not able to, get my head around that.
Okay, it's so I would like you to request ki you just post your question here today, because I am also learning the topic, so it may happen sometime that I couldn't answer immediately. So I also have to think about the thing, because it is the first time I am also learning the graph theory, so I also need some time to think. So if it is possible, you just share the question so that I can at least think about the question. I can get some time to think about it.
Yeah, sure.
Yeah.
Thank you.
others, if you want to see the question, you can like continue, and if you don't have any doubt, then you can leave.
मैम
Yeah.
मैम राहुल को सिर्फ इस बात का कंफ्यूजन था क्योंकि सी के बाद डीएफएस में हम लोग का एफ आ रहा है, तो वो सोच रहा है कि सी से एफ फॉरवर्ड हो रहा है, तो फॉरवर्ड इज क्यों नहीं है। सिर्फ
ओ
तो
अच्छा अच्छा
उसको
अच्छा।
इतना बताना था कि डायरेक्ट अगर कनेक्ट हो तो ट्री है, जो उसको फॉरवर्ड बैकवर्ड गिनेंगे ही नहीं अगर डायरेक्ट कनेक्ट होता है तो। वो सिर्फ इस बात पे
Yeah,
कंफ्यूज
yeah.
था।
So that is why I asked him to see the part of the lecture once again, so that
यस
he
मैम, मिस
can
हो गया,
get.
छोटा सा बात था, सिर्फ यही छोटा सा बात के लिए कंफ्यूज हो गया था। सिर्फ इसी पॉइंट,
Yeah.
वही पॉइंट बताना था उसे। ओके मैम, गुड नाइट।
One more generic question to everyone, like कोई book recommendation है क्या for reading the through the graph theory, or just the lecture is the one that we are actually going through? Anyone is referencing any book which makes the understanding much better?
I don't recall some basic book. If anyone have anything in your mind, you can just suggest.
I also don't recommend any basic book, but there is a channel named Gates Messer. He explains every algorithm very well, like Dijkstra, Wellman Ford. Yeah,
Channel in YouTube, you mean?
yeah, yes, YouTube.
Can you put
One,
that channel name here?
yeah, Gates Messer.
Okay. Thank you. Thank you.
You're welcome.
Yeah. Okay, I'll then disconnect. Thank you, guys. Thank you, ma'am. Bye-bye.